Hello everyone, this is Kunika Chandra from Shivaji College, Delhi University. Currently, I'm in the second year of my course BSc Physical Sciences with Chemistry, and today, as a part of the teacher internship program, I will be teaching a topic of organic chemistry called amines in this lecture. So before we start, let's have a quick overview. So this topic of amines is divided into two parts, and part 1 would be covered in this video, where we'll be talking about amines and their basic classification into 1 degree, 2 degree and 3 degree. Next we'll move on to the method of preparation, which we'll do by 3 methods: ammonolysis, Gabrielthalamide synthesis and Hofmann bromide degradation along with their mechanisms. And in the end we'll do some reactions that amines show, namely Shorten-Bombin reaction and some electrophilic substitution reaction like nitration, sulfonation and halogenation. So let's start with the basic idea behind amines. What are they? So when I take a simple molecule of ammonia, I see that it has 3 hydrogens attached to it. Now, when we start removing these hydrogens one by one with either an alkyl or an aryl group, we start to get amines. So when I remove the first one and replace it with an alkyl group, I get a primary amine. Removing the second one would yield a secondary amine, and the third one would yield a tertiary amine. Now, instead of replacing it with an alkyl group, I can also remove the H and replace it with an aryl group. So in this case as well, we would get an amine. Moving on to the main question on how amines are synthesized. So the first method we will be using is the ammonolysis of alkyl halide. So as the name suggests, ammonolysis means adding an ammonia into the alkyl halide. This is the basic reaction. So let's get into the depth of it. So in this method, 2 cases arise. One is when we have excess of ammonia with this, what happens? Let's see. So we are reacting an ammonia molecule with an alkyl halide molecule. Since the halide is electronegative, it would take the electrons of the bond to itself, leaving the alkyl group positive. Now, seeing this positive alkyl group, the lone pairs of ammonia would get attached to it, making a 1 degree amine salt. Now, as this case suggests that we have excess ammonia with us, so we'll add a molecule of ammonia again, and we will get a 1 degree amine with some quaternary ammonium salt. So this is the case 1. Case 2 suggests that we use excess of alkyl halide. So let's see how this reaction proceeds in this case. So we have the X of alkyl halide, which would take one of the hydrogens from the ammonia to expel HX. And since one of the hydrogens was taken, we are left with NH2, and this alkyl group over here gets attached to give us a 1 degree amine. Now, since we have a lot of alkyl halide to react with, we'll react it again, and this time the X would take another of the hydrogen to expel HX, leaving just one hydrogen over here. The alkyl halide would get attached, giving us a 2 degree amine. Reacting it further with some more alkyl halide would get a 3 degree amine, where no hydrogen is left at all. And then we add more of the alkyl halide. So since we don't have any hydrogen to react with, we would get an R4N plus. Because nitrogen cannot make more than 3 bonds, a positive charge comes over here, and this halide with a negative charge comes and attaches itself, making a quaternary ammonium salt. So when we add excess of alkyl halide, we would get a quaternary ammonium salt. Another method to prepare amines is the Gabrielthalamide synthesis. Through this way, we can prepare 1 degree aliphatic amines only, because when we want to make aromatic ones, it can be made because they cannot go nucleophilic substitution reaction, which is the essential way with which this reaction proceeds. So looking at the basic reaction, when we react ethylamide with an alkyl halide in the presence of alcoholic cleavage, we get N-alkyl phthalimide. And when we hydrolyze the species, we would get 1-degree amine and phthalic acid. So let's see how it's done. So this reaction has just 2 steps in it. Step 1 is reacting ethylamide with an alcoholic cleavage. So this way water gets out and we get potassium phthalimide entity, and then we react this entity with an alkyl halide. So R plus and X negative exist, and that's how K plus and X negative is expelled out, and N minus and R positive would get attached to make an N-alkyl phthalimide. In step 2, the entity we got in the previous step would be hydrolyzed, and so these 2 bonds would break to give us phthalic acid, and the NR would give us 1-degree amine. So this is how we use Gabrielthalamide synthesis to prepare 1-degree amines. Next is the Hofmann-Bromide degradation. So according to the basic reaction, we react 1-degree amide with an NaOH and bromine to get a 1-degree amine. Now, why is it called degradation? Degradation means to degrade, to become less. So when we want an amine which is having 1 carbon less than the parent amide, we use this method. So the reaction mechanism of Hofmann-Bromide degradation has 3 steps in it. Let's start with the first step. So here we have the amide and bromine. The bromine actually has Br negative and Br positive. So the Br negative part would react with this H positive to expel HBr, and the positive Br would go on and get attached like this. In the second step, we are hydrolyzing, so we would get water in this manner, and this entity would undergo a rearrangement process after the expulsion of bromine to get an acyl nitrine. In the third step, this acyl nitrine would again undergo further rearrangements to give us an alkyl isocyanate, and then hydrolyzing it with cleavage, we would get a 1-degree amine. So this is how we use Hofmann-Bromide degradation to get amines. Amines also show a variety of reactions. The first one is the Bombin reaction. So reading what's written over here, it is the benzylation of compounds having an active hydrogen like alcohols, phenols, or amines. So the basis of the Bombin reaction is that it is a nucleophilic substitution reaction. So I'll give a brief at what is this reaction. When we have a nucleophile and it replaces a functional group, this is called a nucleophilic substitution reaction, when the nucleophile replaces or substitutes a functional group to get attached instead. So we will do this Bombin reaction by taking an example of aniline, how an amine like aniline would react with acid chloride in the presence of NaOH to give us N-substituted amides. Let's have a look at the reaction mechanism of the Bombin reaction. So we've taken aniline, and as suggested before, we have to use an active hydrogen compound. So this reacts with benzoyl chloride in the presence of NaOH to give us benzenylide and salt and water. So let's see the in-depth detailing through a mechanism. Step 1 is we are reacting the aniline with benzoyl chloride. The oxygen being electronegative takes the electrons from the double bond to itself, leaving the carbon positive. Now the lone pairs on the aniline would get attracted to this positive carbon, and this is how we get this compound. In step 2, hydrogen would come out from this species, and in step 3, the same species over here would expel a Cl, and the oxygen would return its negative charge to make a double bond. This is how we get a benzanylide. The species left in between of the reactions would react together to make water and NaCl. So this was the mechanism of the Schotten-Bombin reaction. Next set of reactions shown by amines is the electrophilic substitution reaction, and this is specifically shown by the arylamine called aniline. So in electrophilic substitution reaction, the electrophile replaces the functional group from an entity. So let's see how it's done. So NH2 would give the lone pairs of a hair, and this is how the negative charge comes over ortho and para positions. And reading this, we'll see that the NH2 group is electron donating group due to the presence of lone pairs, as we can see over here, and it delocalizes the lone pairs of electron over the aromatic ring, thus activating the ring. Now when we have negative charge over the ortho and para position, it invites certain electrophiles towards it to make different entities. And there are three types of electrophilic substitution reaction that aniline show, and they are halogenation, nitration, and sulfonation, which we'll do in detail in the upcoming slides. The first is halogenation, which is really simple. If we are using a polar solvent like water, the bromine would get substituted on all the sides of ortho and the para position, making 2,4,6-tribromoaniline and expelling HBr. But if you want to have bromine only at the ortho or para position, we will use a non-polar solvent like carbon disulfide. The next electrophilic substitution reaction that aniline shows is the nitration. Now, it's a bit of a problematic reaction for aniline because we're getting 47% of M-nitroaniline. So in the next slide, we'll see what propels this reaction to make such a large amount of meta-nitroaniline. So when we are using the nitrating mixture, which is concentrated HNO3 and concentrated H2SO4, which is strongly acidic, when we react it with aniline, we get an anilinium ion, which is actually a meta-directing group. That's why we're getting such a large amount of 47% of meta isomer. So how do we suppress the formation of this isomer? We would simply use a protection group over one of the hydrogens, like replacing it with a protection group, and we can see that it is actually an acetyl group, so it is called acetylation, the protection of amino group. So looking at the mechanism of protecting the amino group with the help of acetylation. So first of all, we are using acetic anhydride, where acetic acid would be expelled and we would introduce the acetyl group into the aniline. Now we can easily use the nitrating mixture we are having, and we would get ortho and para-nitroaniline and no meta-isomers at all. Now we would hydrolyze them so that this part over here would get out in the form of acetic acid, and we can freely have para-nitroaniline and ortho-nitroaniline. Next electrophilic substitution reaction is sulfonation. So we'll simply use some concentrated sulfuric acid with aniline to get the salt, and when we heat it, we get this entity, but this actually reverts into its Zwitter ionic form and is called as the sulfonilic acid. So this was how sulfonation took place for an arylamine like aniline. So that ends the part 1 of our lecture on amines. Let's take a quick recap at what all we covered. So firstly, we began with the basic definition of amines and how they were divided into 1 degree, 2 degree, and 3 degree amines. Next, we moved on to their synthesis, means how they were prepared. We did it by 3 methods. First being ammonolysis, where we did 2 cases. First was when we used excess of ammonia, and the second where we used excess of alkyl halide. Second method was Gabrielthalamide synthesis, and the third one was Hofmann bromide degradation, where we were producing amines which had 1 carbon less than their parent amide. The next set of reactions we did were some reactions that amines showed. The first one being the nucleophilic substitution reaction called Schotten-Bombin reaction, and the second was electrophilic substitution reaction that amines showed. And we did 3 of them: halogenation, nitration, and sulfonation. So I hope the content of this video was clear, and thank you everyone for watching.